All right, maybe I should zoom a little bit here, see if that would be better. And take the screen down. All right, so let's get started. So last time we finished a bit early because I didn't want to start a new chapter. And this chapter basically is translation, and rotation, of coordinates. Okay, so remember that all this class is directed to think about general equation in solid mechanics and fluid mechanics. So what we did so far is to look at the stress tensor that will help us to represent the stresses, no? In all the different orientation. Obviously, every single structure, you can rotate it, no? So we need to determine what is the deformation that each one of these solids or fluids can be subjected. So so I'm just going to do it here in, I do that like the explanation in 2 dimensionals, but obviously then we will expand into 3 dimensions. So let's say the general equation for motion from kinematics, you can always break it into 2 parts. One part will be due to translation, plus a second part will be due to rotation. That doesn't mean that you need to have both every single time. You can only have translation, no? Like when you go in your car, or you can just have rotation. If you go on whatever, I mean, if you spin something, no? It would just be rotation. Or it can be a combination of both of them. All right? All right. So in 2-dimensional space, just to do some figures because it's difficult to do 3D. Let's say we have a coordinate system. That would be x1, x2, or xy. It would be the same thing, xy. And now we're going to look at the motion into a different coordinate system here. That would be, maybe put here O, would be easier. And this would be O prime if you want x prime 1 or x prime 2 or y prime. Okay? So let's say this has moved a distance in the horizontal direction, let's say h, and on the vertical direction, okay. So we just look here at the translation. So this is only for translation. This is translation. You can define the translation. X equal to x1 will be equal to what? X prime 1 plus h when it moves horizontal. Okay? And if it moves vertical, this would be y, or x2 will be equal to x prime 2 plus k. All right, so this would just take care of the translation. Now, if we just look at the rotation, so we have here x1, x2, or x and y. All right, and now we're going to rotate this. So let's say this will be x prime 1 or x prime, and this will be x prime 2 or y2. Also, it's fine. This will be 1. Okay, shouldn't matter. Just for consistency. Okay. And here we have the point O. So joining this point here, we have O prime equal to O, no? Because they both rotate about the same point. All right. So let's see what happened to a general point here, P. So we have P. Let's do the figure and then I give the relations. So it will be an angle, right angle A. Now we do the projection of this one at a right angle. This will be D. And this point here would be point C. So this angle here is alpha. There's too many things on that figure. So that distance here will be x1. And that distance over here will be the rotation distance, okay? Once you have rotated, this will be x prime 2. Yeah, but I'll call this one x primes. Y, or this would be, sorry, x. This should be the x2. And once you rotate it, become the x prime, no? So if you look at this one, this is parallel to this one. Yeah, so really that distance is x prime 2. Yeah, it's along this one. I don't do it all the way. If you want, you can go all the way here. All right. Okay, so here from simple geometry, I'll give you now the relations that we're going to need. We have that cosine alpha of the angle would be equal to OB. So where is point B over here? Oh, sorry, OB, I didn't put B. This will be here, B. So let me do this one first. Sine alpha, let's see, will be equal to DC. Yeah, will be equal to DC alpha divided by x prime 2. And alpha, so here I forgot to do something here on the figure. This angle here of rotation will correspond also to this angle over here, no? This will also be alpha. So you could say that this alpha here will be equal to OB. So this distance here, OB, so adjacent to the change in height over here, which will be the same as this one over here. So x, so it will be, sorry, x prime 1, where x prime 1 will be, I need to plot it. So what will be x prime 1? X prime will be all that distance here, from here to here. Yeah? Okay, I don't want to put too much, but that will be x prime 1. All right, so basically here we can say that x1 will be equal to OB minus DC, and x2 will be equal to DC will be equal. So let's do the first one here, one at a time. So this will give you, from this figure, will give you OB will be equal to x prime 1 cosine alpha, and DC will be minus x prime 2 sine alpha. So now this one here will be equal to, let's do reverse engineering, will be x prime 1 sine alpha plus x prime 2 cos alpha. So from this one we did the OB to be equal to x prime 1 cosine alpha. So this one we got the DC equal to x prime 2 sine alpha. And I mean, similarly, we do for this one. This will be equal to PC. So the total position of P will be what? PC, the distance PC plus BD. And if we look at the relations, we have the same thing here. We have x prime sine alpha 1 plus x prime 2 cosine alpha. Because what will be PC? For example, here, what will be PC? Will be sine alpha. So sine alpha will be equal to what? PC over x prime 2, no? So similarly, you can find this expression over here. All right? So I don't think I need to write it down, no? Okay? All right. So all this stuff is derivation, but I'm sure you have seen that much this before. Okay, you probably recognize the next equation, or in matrix form. This is a two-dimensional. You have that x1, x2. Is equal to cos alpha minus sine alpha cos alpha. All right, only thing I'm doing is just writing this into the matrix form, no? Cos minus sine, cos, okay? And now the two variables here will be x prime 1, x prime 2. Okay, so this will give you. So this matrix over here will tell you how to go from, if you think about this current system, into this one, no? For rotation. Okay? But we should also be able to do the reverse transformation, to go from this one, the rotated, to the other one. Okay? So without going into too many details, we can say that similarly, you can obtain from the figure that x prime 1 is equal to x1 cos alpha plus x2 sine alpha, and x prime 2 is equal to minus x1 sine alpha plus x2 cos alpha. or again, in matrix form, you will get that x prime 1, x prime 2 will be equal to cos alpha sine alpha minus sine alpha cos alpha. And this term will be x1, x2. So basically, you see that the only difference between these two here is where is the minus sign located, no? Yep, that's the only difference over here. Okay, so this would be 2. So in initial notation, which is what we're interested, we'll have what? Xi, so it will be 1, 2, can be 3, okay, for 2D will be 1, 2, will be equal to beta ji x prime j, where in this case, beta ji is equal to what? Is equal to cosine alpha minus sine alpha cos alpha. Okay, so it would be the equation 1, and the equation 2 will give you x prime I equal to beta ij xj, where beta ji is equal to what? Cos alpha sine alpha minus sine alpha cos alpha. Okay, so over here you can see that beta ji is simply the transpose of beta ij. So if one beta ij or beta ji would be easier to put is the transpose of beta ij. So this will be 1, this will be 2, okay? And you can have this equation, this will be the transpose. All right, but for the specific case, there is something unique about this, okay? That we're gonna do next, is that actually the transpose, in this case, because it's cosine sine, is actually equal to the inverse, all right? So let's prove that. So 37, so let's say using linear algebra, so basically we're going to use the matrices. This means what? X1, X2. I mean, it's repetitive, but will be equal to what? Cosine alpha sine alpha minus sine alpha. Okay, I think I did. It doesn't matter, we can resolve it very quick. It's not going to be a big issue. So let's start with the first one. So let's say this is the primes. x prime 1, x prime 2. I need to change a bit from the notation, and then this would just be x1, x2, no? I'll reverse, but I think I can start from here. But if we start from here, what would that mean? That we just do it from this matrix. x1, x2 will be equal to what? To the inverse of this matrix times x prime 1, x prime 2, no? So this will be cos alpha, sine alpha, minus sine alpha, cos alpha, minus 1. So we move this one to the other side, and this should be x prime 1, x prime 2. Or in initial notation, x prime I will be equal. Remember, we started by beta ij x of I. That's what we started with. And we say that xi will be equal to beta ij minus 1 times x prime j. No? Okay. Basically, I mean, this stuff is so logical that sometimes might be hard to follow, but okay. And recalling from the previous page, what is xy? Is equal to beta ji x prime j, no? Okay. Let's say. And from previous page, we know that x of I is equal to beta ji x prime j, and we say that this was equal to beta ij transpose x prime j. All right, so okay, so we can just write that comparing these two equations, A and B, we get that beta ij minus 1, okay, equal to beta ij transpose. So what is unique about when you have the transpose equals to the inverse? Okay, so that means if you think about this, cosine, look at the figure, what is something unique that we have done over here when we did derivation is that everything is orthogonal, no? So basically that is what this condition is saying, is that if the rotation satisfies that the transpose is equal to the inverse, that satisfies that the two coordinate system would be orthogonal. Okay, so this is basically the orthogonality condition. So the above equations defines the orthogonality of the rotation. So if the two systems are orthogonal and you produce the rotation, this should be valid. Okay? That's basically what it means. So from the orthogonality condition, okay, let me first write it down, general form, and then I do a matrix form. We have beta aj, beta ij minus 1 will be equal to beta ij times beta ij transform, no? Because of the condition. And this will give you what? Will give you 1, 1. No, basically it should give you a diagonal matrix 1. So in the initial notation, remember this will be the delta Kronecker symbol. Symbol, okay? Or we can just rewrite this as beta ik, doesn't matter, you can use different indexes, beta jk equal to delta ij, no? You can do the summation on this one. Okay, so probably we don't need to do it, but let's do it anyway, because it's always easier once you have initial notation. Helps a lot to write down, but doesn't help to visualize anything. I think it just makes it very hard to visualize something, no? That's why generally is not being taught at the undergraduate level. But if we rewrite the same thing here, the equation, so we write the equation, beta ij minus 1 equal to beta ij transpose, this will give us what? Cosine alpha sine alpha minus sine alpha cosine alpha now this one will be for 2D. You just need to what would be this? The magnitude will be cosine squared sine squared, and the inverse will be you inverse one of the diagonals and you divide by the summation of them, no? Which is 1. So this will give you what? The inverse will give you cosine alpha minus sine alpha by using Cramer's rule, sine alpha cos alpha. And this obviously is equal to the same thing if we write under this form, cosine alpha sine alpha minus sine alpha cos alpha cos alpha minus sine alpha cos alpha Okay, what's important to know is what? Is that these two matrices will be equal to what? 1, 0, 0, 1. Oops. Because if you do this, what do you get? Cosine times cosine plus sine times sine, no? Okay, so do this one. So you get 0, 1, 0, 1, which is the so this is the identity so this one is a lot easier to understand that if you do the rotation, so for example, if you move this one 1, it's going to move 1 up, no? So the rotation is always going to remain orthogonal. All right? Okay, so we did the derivation in 2 dimensions, so let's generalize now in 3 dimensions, okay? So the 2D discussion or derivation can be extended to 3D without adding much more information, okay? Without adding much more information. Right. Without adding much more information is a way of speaking, no? Because really it's a lot more involved. I find it very hard to visualize this in 3D, personally, okay? I'm not very good at picturing stuff. But let's say if you have the current system, here we'll have, let's try to do just one figure. Let's say it will be X1, X2, X3, so it will be orthogonal coordinate system following the right-hand rule, no? This will give you now, let's see, we have an X prime 1, X prime 2, and X prime 3. So we have to put a point in space, let's say here, P, would be the vector P. So we'll give for this one, then it will be for this one, and for this one will be in that direction here. Okay, so in that figure, this will be alpha 1. So alpha 1 is rotation about x1. Similarly, you have alpha 2, alpha 3. About x2. Rotation about x3. So this will be alpha 2, and this will be alpha 3, no? Okay, the 3 rotations. Okay, so using same notation as for the 2D case, maybe I can put it here. We have x prime I will be equal to beta ij xj, but this time I equal j, this will be equal to 1, 2, and 3, not just 1, 2. And xi will be equal to beta ji x prime j. So we have this. Okay, and just say that, and the orthogonality condition also remains unchanged. Remains unchanged. Meaning what? That beta ij will still be equal to the transpose, the inverse will still be equal to the transpose, or that we can just rewrite this as beta ik beta jk equal to delta Kronecker ij. So basically, it's kind of easy to follow in 2D, but in 3D it will become a lot more complicated, no? All right? So now I'm just going to give you the value of these beta functions, of these beta matrices for the 3D case. So in 3D, the matrix form of beta ij is given by, so let's see, first we're going to do our rotation about x1, then we're going to look at rotation about x2, and then we're going to look at rotation about x3. So beta ji, I could give you the beta ij, but I think it's more generally, this one is generally used more commonly. This will be 1, 0, 0, 0 cos alpha sine alpha, 0 minus sine alpha cos alpha. And to tell you the truth, to visualize this, because basically when we did the derivation of this, we were able to visualize it because we were able to write, you see, like the change in x was equal to OB minus DC, no? Try to do the plot in 3D. It's a nightmare. I mean, something simple is quite complicated to visualize the angle in 3D, no? For other relations. All right, so then the rotation about x2 will be beta ij, beta ji will be equal to cos alpha 0 minus sine alpha 0, 1, 0 sine alpha 0 cos alpha. And beta ji for the x3 will be equal to cos alpha sine alpha 0 minus sine alpha cos alpha 0, 0, 0, 1. Okay, I want to put the next line here because I think it's important. So a general rotation is given by, so let's say you have a beta ji that you want to do. So let's say you can first rotate about x1, then you can rotate about x2, and then you can rotate about x3 if you want. Okay? Okay, now I'm going to tell you something that you're going to be pretty surprised, but it's true. If you are on robotics, probably you already know it, but if you got a reference frame, let's say you rotate 90% clockwise about x1, then you rotate 90% clockwise about x2, and 90% clockwise about x3, okay? If you do the inverse, you don't end up at the same location. You end up actually is a mirror. You end up down. I don't make sense. Wait, doesn't make sense, no? But because people will say if you do exactly the inverse, you should end up at exactly the same location, no? But actually, when you do in robotics, you end up will be the image, will be the mirror. Okay? So obviously we're not gonna show it now, but I will show how that happens mathematically. But just wanted to say that one application of this that remember be careful is that in robotics or something, when you go from one current system and you go to another one, is not to do just the opposite, to go back to the previous one. All right? Not like that all the time. Okay, so this was page 35, 36, I guess 39. All right, let me now define a different way to rewrite this, which is generally used in textbooks. So basically, I'm just going to redo the same thing, but instead of talking these ones about the beta matrices, I'm going to call about direction cosines. If you did ME501, that's what he uses all the time. Devo, the direction cosines. So direction cosines is, if we define the coordinate system x1, x2, x3, and as before, we have a point P over here. Defined this way. So this will be our vector u. So this will be alpha 1. The same angles that I should have done before should be the same thing. Alpha 2. And now this should be here. Doesn't matter which way you do it. Let's say I do it here. Alpha 3. Okay, so basically here that's said that the vector u in here is equal to u cos alpha 1 e1 plus u cos alpha 2 e2 plus u cos alpha 3 e3. So basically, what will be the coordinates? This is magnitude times directions, no? So coordinates u1 will be u cosine alpha 1, u2 will be u cosine alpha 2, u3 will be u cosine alpha 3, no? And directions will be e1, e2, e3, all right? So we can write this as u equal to u sub I, e sub I. In this notation, or if you want in here, we could say that, what I just said, where u1 will be what? U cosine alpha 1, u2 will be u cosine alpha 2, u3 will be u cosine alpha 3. Okay, and if you want, E1 is would be E1. It doesn't matter. This will be E1 and so on. E2 will be E2 and E3 will be E3. This remains unchanged. Okay, or this one you can also rewrite it. So if U sub I is assumed unity, so basically U equal to 1, 1, 1, then you have that U sub I equal to cos alpha sub I. Okay, so this means assumed unity. That means that U equal 1. Hold on 1 second. And this is basically what is called the direction cosines. Okay, so similarly, as we just derived here for the vector U, similarly as for vector U, the unit vectors can be written in function of direction cosines. So basically, you can just say that EI will be equal to AIJ E of J, it should be. So this means that E1 will be equal to A11 E1 plus A12 E2 plus A13 E3. E2, so this will be, sorry, the E primes, when you do the rotation, no? Same thing, will be equal to A21 E1 plus A22 E2 plus A23 E3. I'm just substituting here. Here, I forgot to put the prime. This would be the rotation, no? Same as before, we had X prime. These are just due for the unit vectors of the current system. So will be equal to E prime 3, A31 E1 plus A32 E2 plus A33 E3. Okay, so let's get there. A little bit more, and then I'll stop for a second and we do a summary. So this was page 39, page 40. Okay, where in this equation we can say that Aij in matrix form is equal to what? A11, A12, A13, A21, A22, A23, A31, A32, A33, and this is equal to what? cosine alpha 1 1, cosine alpha 1 2, cosine alpha 1 3, cosine alpha 2 1, cosine alpha 2 2, cosine alpha 2 3, cosine alpha 3 1, cosine alpha 3 2, cosine alpha 3 3. Okay, so if before we had this relation here, okay, so if we had E prime I equal to A I J E J, okay, if you want, let me write it down. This equation is similar to this one. This one is kind of similar to X prime I equal to beta IJ XJ, no? Okay. So similarly, we can have what? We'll have that EI will be equal to A Ji if the orthogonality condition is satisfied, no? E prime of J. Okay? So this means if system is orthogonal, the above is satisfied. Okay? And what does that mean? That E prime of I dot E prime, or E prime of I EJ, so the two vectors, this one and this one, what should happen to these two for this to be equal? This needs to be equal to 1, no? Yeah, so it will be delta IJ equal to 1. Which is basically, should give us the same condition as we had on the identity matrix before. All right, so here what you need to remember is that now we have two forms of writing down everything. We have this form, or we have the xi equal to beta, what do we use? Ji x prime of j, no? So these forms are kind of equivalent, but you see that really they are not represented by the same thing, because on the first case, when using this one, what were all these matrices we're using? We use sines and cosines and 0, 0, 1, no? Another form to re-say exactly the same thing is by using the direction cosines, and now you need to know all the different angles. So each one has advantages, the other one has disadvantages, okay? But this is generally the one that is more generally used in the textbooks. I think this one is better to write down the equations or the formulations. I think it makes more sense. But once you go to the real application, generally this is the one that is being used. Okay? So I had a note here, my notes. I'm going to put it here. So notes. Check. MATLAB commands. DCM, which I guess means direction cosines to angles. So I think basically, I'm kind of guessing this one should go, let you go from these ones here, alpha 1, 1, to give you these angles alpha 1, alpha 2, alpha 3. Yeah, I think that's why you should do that command. So I have that one and the opposite, which is angle to DCM. So I guess that you can get the angles from the direction cosines, or you can get the direction cosines from the angles. I don't know exactly how to use these ones. All right, so let's do a simple example here. How much time we have? 17 minutes. Let's try to do it. So page 41. So example, let the prime axis of prime x prime 1, x prime 2, x prime 3 be rotated 45 degrees counterclockwise about x2 with respect to all x1, x2, x3. I mean, this is very simple. We need to determine the prime components of the vector v equal E1 plus E2 plus E3. Okay, so what we're going to do here, the goal over here, see if we can finish, is to solve this problem using the two different approaches, no? This one, the red equations, and this one, and we should get the same thing, okay? All right, so let us solve using notation. So let's say the vector here will be, this will be the x prime I, will become v prime I equal to beta ij dj, no? Okay? Where if we do the rotation about x2, what is that page here? I don't know where it is. Ah, here it is. If we do it about x2, which matrix should we use? This one over here, no? Okay, rotation about x2. So in this case, rotation about x2, we have that beta ji is equal to cos alpha 0 sine alpha 0 1 0 minus sine alpha 0 cosine alpha. Okay, or I could just rewrite it in function of ij. Well, that would mean what? That the lines will become the columns, no? So it will be cos alpha 0 sine alpha. Then this one will be unchanged. And now the last one will be minus sine alpha 0 cos alpha. Yeah, that's correct. Okay, so for alpha equal to 45 degrees, what do we have? Beta ij. So cosine 45 will be square root of 2 over 2, 0, square root of 2 over 2, 0, 1, 0, minus square root of 2 over 2, 0, square root of 2 over 2. Almost done with this one. So now we can substitute back into this equation. Okay, so we have, so that V prime I equal to beta ij Pj will be equal to what? We put in matrix form, we'll have V prime 1, V prime 2, V prime 3. Beta ij will be square root of 2 over 2, 0 minus square root of 2 over 2, 0, 1, 0, square root of 2 over 2, 0, square root of 2 over 2. Okay, and our vector V1 is 1, 1, 1. So basically, this gives that V prime 1, V prime 2, V prime 3 will be equal to what? If we do the first one, what do you get? You will get square root of 2 times 1, 0 minus 1, 0, no? Yeah? For the second one, what will you get? You will get 1. And for the last one, we'll get this one plus this one, so 1/2 plus 1/2, we'll get square root of 2. Okay? Okay, so now, next, let us solve the same problem using direction cosines. So this one is a lot more difficult. I mean, I don't know, it's whatever. Each one has an advantage and disadvantages. So let's say here I do the plot. I don't know why I did it this way, but there's probably a reason. So let me leave it unchanged. I know why I did it that way, because, okay. So x1, x2, x3. So we rotate about this one. So it's hard to see now. We rotate about this one. So this one is going to be rotated x prime 3, 45 degrees. X prime 1 with respect to this one will be rotated 45 degrees. And now remember, this one is being rotated here, but this one is being rotated this way, no? So really, this would be x prime 2, okay? Everything is rotating that way. And let's say we have our vector v over here. So we know the angle about x2 will be this one here. The angle between x3 will be this one here. And the angle to x1 will be this one in here. All right, so here you do, that's what I have the hard time to visualize those things. But if you were able from the figure to rewrite what would be the matrix Aij, this is what you will have. You will have cosine, let's see, cosine alpha 1, 1, cosine alpha 1, 2, cosine alpha 1, 3, cos alpha 2, 1, cos alpha 2, 2, cos alpha 2, 3, cos alpha 3, 1, cos alpha 3, 2, cos alpha 3, 3. Okay, so here we need to be careful because this is the difficult part here. Alpha AB, the angle, means this is the prime axis. And this will be the unprime axis. Right, so this is the difficult part that I always have a hard time to visualize, but basically if you do alpha 1, 1 between x1, between x prime 1 and x1, what is the angle is 45, okay? Now, between 1 and 2, so 1 and 2 over here, again, it's hard to visualize those things, this will be 90. Now, 1, 3 is this one all the way to this one, so it's all this line here is 135. It's 90 plus 45. Okay? 2, 1, similarly, will be 90. Then this one, what would be this one? 0, because they are on top of each other, they are coplanar. Then this will be 90 because now 3, 1, this should be now 1, 3, 1, 3. This one is given to be 45. 3, 2 is 90. And 3, 3 is 45. So basically you get Aij. Okay, so cosine 45 is square root of 2 over 2. Cosine 90 is 0. Cosine 135 will be, you go to the other side of the circle, so it's minus square root of 2 over 2. And similarly, we have here cosine 90 is 0. Cosine of 0 is 1. Cosine of 90 is 0. Cosine of 45 will be square root of 2 over 2. Cosine of 90 is 0. Cosine of 45 will be square root of 2 over 2. Okay, so let's see, we'll go back to the matrix. So if you think about it, maybe we have to do it now, but we end up with the same beta ij that we had before, no? Okay, so can just say here, which is equal to beta ij as expected. That way we don't have to do the calculation on the other page. Is that okay? You want me to find the 101 or whatever we found before? It's the same thing, no? Okay. So basically, which one is easier? I have no idea. Do you want to use direction cosines? You can use direction cosines. You want to use the other type of matrix where you have the beta given to you depending on the rotation, and it's fine. Okay. What happened here? I'm going to tell you the truth because we only do rotation about one axis. But if you start doing rotation about multiple axes, then this becomes even harder, no? You always need to do about one axis and then do the other ones. All right, so we stop over here. And now the next thing to do is to go